optimizing transportation costs using matrix multiplication and inverse matrix. Introduction. Efficient transportation planning is key to reducing operational costs in supply chain management. This case study demonstrates how mathematical concepts such as matrix multiplication and inverse matrix can be used to develop an optimized transportation model. The goal is to ensure demand is met while minimizing total transportation costs. Matrix multiplication used to calculate the total cost of a specific transportation plan. For example, multiplying the cost matrix by a matrix representing the number of units shipped between origins and destinations yields the total cost. Inverse matrix, useful for solving linear equations that represent the constraints of the transportation problem. By finding the inverse of the coefficient matrix in the linear system, one can determine the optimal allocation of goods to minimize transportation costs.
The purpose of this study are solve real-world transportation problems. It's to determine the optimal allocation of goods from sources to destinations to minimize transportation costs. Then, showcase the use of linear algebra in decision making to illustrate how inverse matrices can help find unknown shipment values or adjust cost structures. Next, apply metric operations in optimization to use matrix multiplication to compute total transportation costs for given routes and shipment quantities. And lastly, educational and practical insights. It gives insight into using mathematical tools for cost-effective decision making.
Methodology. 1. Problem identification. Identify supply points, demand points, and the cost of transportation between each pair. 2. Matrix construction. Create cost matrix C contains cost per unit from each source to each destination, supply vector S and demand vector D. 3. Mathematical formulation. Represent the transportation problem as a system of linear equation. AX equal to B. A for coefficient matrix, X for transport quantities, B for supply and demand value. 4. Matrix inversion method. If matrix is invertible, solve using X equal to A minus 1B. 5. Cost calculation. Compute total transportation cost using total cost equal to C multiply S. 6. Validation. Check if all supply and demand constraints are met, all transport values are non-negative, and compare with traditional methods if needed.
Now, let's move to discussion part. Here is example question for transportation problem setup. A company operates 2 factories and supplies products to 2 stores. The cost to transport 1 unit from each factory to each store is provided in a table. Factory 1 can supply 70 units and Factory 2 can supply 80 units. Meanwhile, Store 1 requires 60 units and Store 2 needs 90 units. The goal is to determine how many units each factory should send to each store while minimizing transportation costs. As you can see here, there are 3 questions that we need to answer based on the transportation problem statement. First, use the matrix inversion method to determine how many units each factory should send to each store. 2. Calculate the total transportation cost. And lastly, validate the solution. Now, let's see the steps to solve each question. Step 1. Identify key elements. We identify the supply points as Factory 1 and Factory 2, and the demand points as Store 1 and Store 2. transportation costs are given for every pair of supply and demand points. We need to find the best way to distribute units from factories to stores while meeting supply and demand limits. Step 2. Build the cost and constraint matrices. We represent the transportation cost in a matrix form. Then, we define variable x1 as units from factory 1 to store 1, x2 as units from factory 1 to store 2, x3 as units from factory 2 to store 1, and x4 as unit from factory 2 to store 2. Next, we create the supply constraint and demand constraints using equations that match the capacities and needs. Step 3. Create the linear system. We convert the constraints into a system of linear equations and represent it as a matrix equation, where matrix A represents the coefficients from the constraints, X is the vector of unknowns, and P is the supply and demand values. This sets up the problem for solving using matrix methods. Step 4. Solve using matrix inversion. We solve the equation using the formula, which involves finding the inverse of matrix A and multiplying it with matrix B. The result tells us how many units to send from each factory to each store is 40 units from factory 1 to store 1, 30 units from factory 1 to store 2, 20 units from factory 2 to store 1, and 60 units from factory 2 to store 2. This solution meets all supply and demand requirements efficiently. So, the first question settled.
Next, we will move to the step 5, where we will calculate the total transportation cost. Using the cost matrix, matrix C, we will multiply with matrix X, the transport values, and we will get the total transportation cost, which is 470 ringgit. Last step is the validation, where we have to substitute X1, X2, and X4 values into the supply equation and demand equation. And here, it is proven that the total sent from each factory equals the supply, and the total received at each store equals the demands. And also, all transport values are non-negative. So, that's all in this part, as we have solved all the problems. In conclusion, in this case study, we explored the practical application of matrix multiplication and inverse matrix methods in solving a transportation problem. By formulating the problem using matrices, we were able to represent complex supply-demand relationship and transportation costs in a structured mathematical form. The use of matrices in this context highlights how linear algebra can be applied to real-world decision-making, especially in fields such as logistics, supply chain management, and operation research. This shows the importance of mathematical tools in optimizing resources and supporting strategic planning in industries. So, that's all from our group. Thank you.